Bezier curves. Bezier curves are very popular. So usually when people tell you something about a curve, it's usually a Bezier curve. So these Bezier curves, they can be constructed procedurally. So there is this algorithm where we take, let's say, 4 control points and we interpolate lines between those points. So we kind of subdivide these lines that connect the control points. And we again have this variable t that goes from 0 to 1. So when t is 0, then this subdivision it's in the beginning of each of these lines. And when t goes to, let's say, 0.5 and now to 1, then these white like subdivision points, they go along these lines here. And now we do it recursively. So we join these points that are traveling along these lines and we get new lines. So initially we have these 3 lines. When we connect them, we get 2 lines, and we're going to interpolate along those 2 lines the same way. We get 2 new points, we get 1 more line here, and when we now have this last point that is traveling along this last line here, well, that point is going to be a point that is on the curve. So this is how this curve is constructed in this procedural way. Now this algorithm is called the Castellios algorithm. And well, here's another animation of it. So you can see that these lines kind of move along these outer lines according to the parameter t that goes from 0 to 1. And the point on the last line is going to get us this curve here. Now we started with this constructive procedural algorithm instead of specifying the constraints. So the question arises, what would be the constraints? So well, we can kind of see that maybe it passes P0 and P3 always. But we also have this P1 and P2. So what are these affecting, and what exactly is happening with these Bezier curves? So let's try to find these constraints. Let's find them from this constructive algorithm. So we had these points P and we had these subdivision points. So the points that are traveling along these lines. So those would be Q0, Q1 and Q2. And well, the equation would just be this, that if we have our parameter t, if it's 0, then we have Q0 equals P0, but then it's going to be a linear mix between P0 and P1, so this Q0 is traveling along this line from P0 to P1 linearly. And recurse. So we have these points R0 and R1 now, that are on the lines from Q0 to Q1 and Q1 to Q2, and these are also linearly interpolated. And we had this last point, let's say S0, so that's on the curve, but that's a linear interpolation between R0 and R1. Now if we write all of this out, then we get a line like this. So this S0 is actually going to be this combination of P0, P1, P2 and P3 with these specific coefficients. And you find these just by putting together these equations here. Now we have this row, and from this row we can very easily detect the blending functions. So the factor for P0 is just 1 minus t cubed, and that's our blending function 0. Similarly, our blending function 1 is over here, that's the factor for P1. Our blending function 2 is over here, that's the factor for P2. And our blending function 3 is over here, that's the factor for P3. So we actually now know the blending functions for our cubic Bezier curve. So let's write these out. So how much t to the power of 0 do we have? How much t to the power of 1 do we have? T squared and t to the 3rd power. Because now we can easily put them into the blending matrix. Blending function number 3 is the 4th column. So we have 0 times t to the 0th power plus 0 times t to the 1st power plus 0 times t to the 2nd power plus 1 times 3 cubed. So it's going to be 0, 0, 0, 1. Or our blending function 0, well, that's just going to be up here. It's going to be 1, minus 3, 3 and minus 1. Exactly this column here. And now that we have created this blending matrix from the blending functions that we found from the Castellios algorithm, we can find the constraint matrix. Just like the blending matrix was an inverse of the constraint matrix, the constraint matrix is an inverse of the blending matrix. So we just take the inverse and we find this constraint matrix. Now remember, this constraint matrix was used to multiply with the vector of unknowns to get the control points. So let's multiply this constraint matrix with our vector of unknowns. So we find that P0 must equal A0, P1 equals 1/3 of A1 plus A0, and so on. Now these are the equations for our constraints. So let's see what they mean. We have this larger curve equation, so it's a cubic Bezier curve. We have a cubic function. And just like before, we have these unknowns, A3 times t cubed plus A2 times t squared and so on. And now looking at this equation and looking at these constraints, we can start figuring out what exactly these constraints mean. For example, if we take the curve at 0, then, well, this t is gonna be 0, this one as well, we get A0. So all of the terms cancel out and A0 is left. So curve at 0 is just A0. But up here we saw that A0 equals P0. So this constraint now tells us that at the beginning of the curve has to be at P0. This is exactly what we saw on the curve as well. It started at the first control point. Its location was at P0 when we started the curve. Next, we can see what happens when a curve equals 1. All of these t's will become 1, and we will have A3 times 1 cubed plus A2 times 1 squared and so on. This is just going to be A3 plus A2 plus A1 plus A0, and we had this constraint also in the constraint matrix. So this must equal P3, which means that the curve ends at P3. When t equals 1, then we have the value P3. So now we already have found those two, well, perhaps obvious constraints, that the curve must start at P0 and end at P3. Now we might venture a guess that, well, maybe the other constraints are somehow related to the derivative. So let's find the derivative of our curve function. So to find the derivative, we take the derivative here. This is gonna be 3 times A3 times t squared plus 2 times A2 times t plus A1. Now let's see what value our derivative has at 0. So the curve's derivative at 0, well, everything will go to 0 except A1. So this is gonna be A1. Can we somehow get A1 from these constraints? And the answer is, well, yes, we can. So A1 is over here. And we also have this A0 here and A0 here. So we want to get rid of A0 to get this A1. Well, it's 1/3 of A1 as well, but let's just focus on getting this A1. So basically we can subtract from P1 P0. If we do that, these A0s will cancel out and we have 1/3 A1. But the curve's derivative at 0 is just A1, which means that we also have to multiply it by 3. So it tells us that our derivative is actually 3 times P0 minus P1. So we can take the vector from the first control point P0 to the second control point P1, and that is basically just 1/3 of the derivative. The actual derivative being 3 times longer than that line segment. Now we can do a similar thing at curve's derivative at 1 at the end of the curve. So we can see that, well, all these t's will become 1s. So we have this 3 times A3 plus 2 times A2 plus just A1. And well, we have all of these a's over here for P3. And we also have this P2. So maybe it's similar to the first derivative. So if we just subtract those two, then from P3 we subtract P2. Well, A0s will cancel out. And we will have like 1/3 A1 and 2/3 of A2 and 1 times A3. But the derivative we have for the quadratic equation here, this is 3 times larger than that subtraction. So the derivative at the end is also going to be 3 times the vector from P2 to P3. Visually this looks like this. So we have the first constraint here, the curve must be here at the beginning, and the last constraint here, the curve must be here at the end. And well, we have these points P1 and P2, but the derivative here is going to be 3 times larger than the vector from P0 to P1. And in the end, it's also going to be 3 times larger than the vector from P2 to P3. It turns out that these blending functions for Bezier curves, they're called the Bernstein basis polynomials. So there is this system of polynomials. Well, there's this general case down here, and you can basically interpolate or blend together some n values using these polynomials, and for Bezier curves it turns out that these are the polynomials that are its blending functions. There are some useful properties for Bezier curves. First of all, the curve here is always inside the convex hull made up of the control points. So any control points you have here, no matter how you arrange them, if you take the convex hull, you are certain that the curve is always going to be inside there. And this is a pretty good property, because if you fix some control points, you can assume that the curve is going to be in there no matter what control points you set, instead of like going somewhere very wild and going outside, doing some weird shapes and then coming back into the convex hull. No, it's always going to be entirely in the convex hull. So it behaves very nicely in that regard. There is also the property of affine invariance. So if we do affine transformations on the control points, for example, we scale them, or we share them, or we rotate them. Well, scaling, I guess, is the most intuitive example there. If we scale those control points, it doesn't happen that the curve somehow starts behaving weirdly or differently. No, affine invariance means that if we scale the control points, then the curve is going to behave as if itself was also scaled the same way. Again, another very useful property. Now, when it comes to splines, we can put together Bezier curves in a spline in a way that we can achieve sufficiently smooth splines. How to do this? Well, there is this Stark's construction, which we're going to see later on in the Bezier spline task. Bezier curves are very widely used for fonts, animations. When you take a pen tool in some vector graphics software, for example, and create a curve, then the chances are that it's actually the Bezier curve that you're creating there. Now, from this video, you should understand the Bezier curves, the Castelliau's procedural algorithm, this recursive algorithm where we just interpolate along the lines, create new lines, interpolate along those until we are left with just one line and one interpolated point, and that's going to be the point on the curve. You should now know about the constraints in the Bezier curve and how you can find them from the Castelliau's algorithm. So the constraints were on the locations at the beginning and end, and the derivatives. So the actual derivative was 3 times larger, the vector from the first control point to the second, and similarly from the third to fourth. You have now seen how to determine the constraints given a procedural algorithm, and you also learned several useful properties of Bezier curves.